Okay, so you should be at the top of page, let's see, 17? All right, so you should be at the top of page 17 with me today. I just told you, second period, this is probably my least favorite section of the notes, so you will not have a quiz on exercise 17, 18, or 19. All right, we're just going to try to get through this. Exercise 17 is really long. So again, if you're one of those people that likes your notes very neat and organized and all that kind of stuff, you may want to do it on a piece of paper and then just keep that piece of paper with that exercise because it's going to get really lengthy. So we already talked about yesterday about how we have polyprotic acids that can donate more than one hydrogen, but they don't do it at the same time. They do it in separate reactions. So when that happens, the first Ka is always the largest, because that's always the strongest acid out of the three, and then the acids get weaker and weaker, so my Ka value goes down. So, except for H2SO4. So H2SO4 is an exception, and we're going to talk about that for why in just a second. Polyprotic acids have a Ka2 and a Ka3 value so much weaker than Ka1 that the second and third dissociation can be ignored. Okay? The hydrogen that is obtained from the second and third dissociation is negligible compared to the hydrogen from the first dissociation. So, what do we mean by that? We just mean that when we have a polyprotic acid, remember, except for this one, H2SO4 is our exception. When you have a polyprotic acid and they ask you for pH, the pH comes from the concentration of the hydrogen from the first dissociation. Okay. Now that doesn't mean that they can't ask you more questions about that second and that third dissociation, okay? But it means as far as the pH is concerned, it would only come from the concentration of hydrogen from the first one. Everybody got that? Do you understand? It was a lengthy paragraph just to say that one thing. Because, here comes our exception, because H2SO4 is a strong acid in the first dissociation, and a weak acid in the second, we have to consider both of the concentrations of hydrogen. So we can't just go with the first one. We have to consider that both of them if the concentration is more dilute than 1 molar. Okay? Now, if it is 1 molar or greater, we can ignore the second one. Okay? And we can just go with the first one. But if it's less than 1 molar, then we have to do it. Here's the good news for you. All right? The quadratic equation would be needed to work this type of problem. What do they not put on the AP exam? The quadratic equation. So I'm going to show you. That will be exercise 19. I'm going to show you, but I'm going to keep it short, sweet, simple, and we're not going to stress about it. Okay? So that's what we're going to go with now. All right, exercise 17 is the lengthiest one we will do today. So just hold tight. All right? Exercise 17 says calculate the pH of a 5 molar H3PO4 solution, and we want the equilibrium concentrations of H3PO4, H2PO4 negative, HPO4 negative, and PO4 negative. Okay? So here we go. We ready to go? We're ready to go. All right, so H3PO4, strong acid, weak acid. Weak. It is a weak acid. So therefore, we already know automatically, right, that we're going to have a what? Price table. I'll talk to myself today. It's cool. All right, so we have H3PO4 that's going to go back and forth to H positive plus H2PO4 negative. We all agree with this?
Yes.
Yes, we all agree with this. Now remember, because it's an acid, I can leave out water. If it was a base, I would want to what? Put water on the reactant side so I could see what was going on. But with an acid, it's easy. I can take water out. My initial concentration was 5.0. My products were 0 and 0. I lost X. I added X. I added X. So at equilibrium, we were at 5.0 minus X, X, and X. Yes? Yes. All right. To find the pH, I have to know the concentration of what? X. Because I've got to know my concentration of my hydrogen, right? So I've got to figure out X. How can I figure out X?
Your product of reactants.
My products over reactants. Okay? I would say Ka1. Why am I specifying that this is Ka1?
Just the
First
first.
association.
Because it's the first association. So the first association is going to be the concentration of hydrogen times the concentration of H2PO4 negative divided by H3PO4. Now, I told you yesterday we would need this, that I didn't just make up these values, and I didn't. What is Ka1 for H3PO4? 7.5 times 10 to the negative third. I just want to show you, I got it off the page before. I'm not just making up numbers. So 7.5 times 10 to the negative third. So we would say 7.5 times 10 to the negative third is equal to x squared over 5.0 minus x. What am I going to do with that x? I'm going to neglect it. So then I would cross multiply and say 7.5 times 10 to the negative third times 5. 3 point, and I did 7.5 in my notes. You can do 3.8. It's not a big deal, so I can change your answer. I get x squared is equal to 3.7 times 10 to the negative 2. So then when I take the square root of that, I get that x is equal to what?
1.9.
There you go. So we just get 0.9. And since we're dealing with concentrations, my unit there would be molarity. Okay?
Do you want us to leave it in decimal form or put it in scientific?
Either one. It doesn't matter. You can leave it in decimal or scientific. If I don't have a 0 something, I normally just leave it in decimal form. But that's just me. It's just easier for me to see. I don't like scientific unless I have to. But you do what you want to do. It's not going to affect your answers in any way. All right? So, what did X give me the concentration of? My hydrogen ion. And what else did it give me my concentration of? The H2PO4 negative. So, I already found H2PO4 negative right there. So, that's one thing I already found that they asked me to find, right? The concentration of my H2PO4 negative. Now that I know what X is, what else can I find the concentration of at equilibrium? My H3PO4, right? So is at equilibrium, here's my E, C, I. At equilibrium, it's 5.0 minus X. So I would just do what for my H3PO4? I would just say 5.0 minus 0.19. And that would give me, since I'm trying to keep my answer in how many sig figs? 2. That would just give me 4.8 molar. So now I found that one as well. There you go. I can also get the pH because the pH only comes from my concentration of hydrogen from the first association. So since I have X and I have my concentration of hydrogen, to get my pH, I can just do pH is equal to opposite the log of 0.19. So then I get my pH is 0.72. Remember, we had 2 sig figs up here. So that means my pH needs to be in 2 decimal places. Some of us are forgetting that, and we are losing points on quizzes. Okay, don't forget that.
When we're doing the problem, do we also round off the two decimal places if it has like 2 sig figs? Or do we just keep all the numbers and just round off at the end?
I normally keep all the numbers in my calculator and then just round at the end. But it doesn't technically matter, to be honest with you. They will know if you did it right and if your answer is correct, or if you did it wrong and you got something incorrect. So whatever you're the most comfortable with. Okay. The only drawback comes like when you write out your work here. Like I said, x squared is equal to this. So then when I get x, technically I should have just went with this in my calculator since I told them that this is what I did. That makes sense? All right, so now we found the first three. Now we've just got to find my equilibrium concentrations of HPO4 2 negative and PO4 3 negative, right? I've got to set up another rice table. You're correct. Because now to get HPO4 2 negative, I'm going to have to go through what? A second dissociation. Okay? So now I'm going to have to show that. And so I'm going to come down here and show it. I'm going to run out of room pretty soon. All right, so now I would say, okay, so my second reaction is going to be H2PO4 negative goes back and forth into H positive plus HPO4 2 negative. Where I now know initially
In this equation, would you have like the water?
Huh? you could show water if you wanted to, but you don't have to. Because it's still an acid.
It's just hard to see like the H2 and something because it's all like that.
Yeah, it's okay. And this time I'm not going to do a rice table, so we can save some time. All right, and let's just go ahead and set it up. So I know my Ka2 is going to be equal to what? Divided by the concentration of H2PO4 negative. Now, do I know most of these?
Yeah.
Alright, so I go back and I pull my Ka2 from the previous page. So my Ka2 is 6.2 times 10 to the negative 8. Okay, so this is 6.2 times 10 to the negative 8 is equal to, do I know my concentration of hydrogen? Yes, my concentration of hydrogen is what? 0.19 molar, because I already found that, right? I'm looking for my concentration of what? My HPO4, so that's my X. Divided by, do I know my concentration of my H2PO4 negative? Yes, we already found that earlier, and it is what? 0.19. So what do these 0.19s do? They cancel out. So what is my concentration of my HPO4 2 negative here? 6.2 times 10 to the negative 8. Do we see that? How that worked out? So these two are equal. So this is equal to my concentration of HPO4 2 negative.
Will it usually be like that?
Yep. It usually will. So now I've also found my concentration of my HPO4 2 negative at equilibrium. Okay. So to get my PO4 3 negative, I'm going to have to go through a what? I'm going to have to go through a third dissociation. So this time I'm going to be going from HPO4 2 negative is going to be dissociating into H positive plus PO4 3 negative. So I know my Ka3 is going to be equal to concentration of my hydrogen times the concentration of my PO4 3 negative divided by the concentration of my HPO4 2 negative. So I go back to the page before. I pull my Ka3 value, which is 4.8 times 10 to the negative 13th.
So the one that cross out like that on the second one.
Is equal to, do I know my concentration of hydrogen? Yes, 0.19. Do I know my concentration of PO4 3 negative? Nope, that's what I'm looking for. Divided by, do I know my concentration of HPO4 2 negative? Yes, we just found that over here. It's 6.2 times 10 to the negative 8. So now can I solve for X? Absolutely. So I'm going to cross multiply here. And do 4.8 times 10 to the negative 13th times 6.2 times 10 to the negative 8th. And what do you get?
2.972.
times 10 to the negative 20th is equal to 0.19 times x. So then to get x, I'm going to divide by 0.19, and I should get x is equal to
1.57.
and so if I round that to 2 sig figs, I get 1.6 times 10 to the negative 2.
So it's just pH that you do like the decimal.
Yes.
Oh, yeah.
So now I found my concentration of my PO439. I'll scroll back down. The mover still working. Sorry, my bad. So is it hard?
No.
Not really. Okay. Is it a lot of steps?
Yes.
Absolutely. Okay. But it's not hard. That's what you need to see. Again, it's one of those things where it's tedious work and it's work that seems to go on and on and on, but it's not impossible for you to do, and you can do it. You can. Don't worry, you're not even going to have homework on this, okay? We're not going to do homework on this one. We're not going to quiz on this one. So don't be freaking out about this. Just go with it. Yes, sir. Yes, sorry, my bad. Thank you, Sean. What are we doing?
Shoulders hurting too.
All right, we ready to move on?
Yes.
Okay, I'm going to clear the ink from this page because I wrote all into my exercise 18. All right, exercise 18, the pH of sulfuric acid. This says calculate the pH of a 1.0 molar solution of H2SO4. So is this solution more dilute than 1.0?
No.
No, it is 1.0. This is what kind of acid? A strong acid. So I know it is going to completely dissociate, and I don't even have to worry about the second dissociation since it's 1.0. Okay? Does this make sense? Are you with me? So that means the concentration of my hydrogen is going to be what? 1.0. Remember, if I have a strong acid, the concentration of my acid is the concentration of my H positive, right? Okay. The only exception to this rule is H2SO4 if it's more dilute than 1.0, but this isn't more dilute, this is 1.0. So all I have to do to get the pH is say pH is equal to opposites alike of 1.0, and if you put that in your calculator, you should get 0. How many sig figs are here? 2. So that means I have to have how many decimal places? 2. So I add 0.00. Because you know 0 and 0.00 are way different. Way different. That was sarcasm, for those of you who can't see my face. Alright. We're good on this? Do we understand why we didn't have to do anything else for this? Okay. Now, the tricky part comes on exercise 19. So the tricky part comes when we realize that they asked me to calculate the pH of an H2SO4 solution when the concentration is 1.0 times 10 to the negative 2 molar. So is this more dilute than 1 molar? Yes. So in this case, I would have to account for both dissociations. Okay? Now, the first time's easy. Because the first time, it's going to completely what? It's going to completely dissociate. So whatever this concentration is equal to what? The concentration of my H plus. So I can say for my first dissociation, I know that the concentration of H positive is equal to 1.0 times 10 to the negative 2 molar. We got that? I didn't confuse anybody about that. Is the first time, no problem, that first hydrogen comes completely off of the first one. So now, what am I left with as my next reactant? Excellent. I'm left with HSO4 negative, right? And so then that's going to dissociate into H positive plus SO4 2 negative. So now I'm going to have to do the Rice table because now this has become what kind of acid? A weak acid. Now remember, I'm going to draw this first one up here right quick so you can see this. There was my first dissociation, okay? And I ended up with 1.0 times 10 to the negative 2 molar hydrogen, which means I also ended up with what?
The same amount of HSO4.
The same amount of HSO4. So do I know my initial concentration of HSO4 negative? Yes. It's 1.0 times 10 to the negative 2. Do we all see that?
Yes.
Do I know my initial concentration of my hydrogen?
Yes.
Yes. It's 1.0 times 10 to the negative 2. Have I lost anybody yet? Nope. Okay. And so my SO4 2 negative is starting out at 0. So when I change, I would subtract x here, add x here, add x here. So I'd be at 1.0 times 10 to the negative 2 minus x. 1.0 times 10 to the negative 2 plus x. And x. So then I would set up my Ka. So my Ka2 would be equal to the concentration of hydrogen times my concentration of SO4 2 negative divided by my concentration of SO4 negative. And to get my Ka2, I'll come back to this page again, just so you know I'm not making up numbers. Here's my sulfuric acid. The Ka1, they just told me it's very what? Large. That's how I know it just completely dissociated the first time. And my Ka2 is 1.2 times 10 to the negative 2. Do we see this? So I say 1.2 times 10 to the negative 2 is equal to my concentration of hydrogen at equilibrium is 1.0 times 10 to the negative 2 plus x times, I don't know my concentration of SO4 2 negative, it's x, divided by my concentration of HSO4 negative at equilibrium is 1.0 times 10 to the negative 2 minus x. And since this Ka value and this concentration are so close in number, I could not neglect x here. So if I can't neglect x, I would have to use the what? Quadratic formula. Okay? But we don't have to use the quadratic formula. Okay? We're just going to solve for x. So the concentration of x would be 0.0045. So I would take my original concentration of hydroxide, which is 1.0 times 10 to the negative 2 molar, and I would add it, okay, to my new x, which is 0.0045, to get my total concentration of hydrogen. Does that make sense? I've got to take it from both of them. So my total concentration of hydrogen would be 0.0145 molar. So now would I be able to get the pH? Yes? Yes, sir.
Yeah.
I didn't solve for x. Okay? I would have had to put that in the quadratic equation and done all that crazy stuff. So we didn't solve for x, I gave you x. I just gave it to you. We solved for x in our calculator, hypothetically, pretend-wise. I just gave you x right then.
Will you always give us X? We have it on my test.
There will not be a quadratic on your test. That's why I'm not making you go through all the steps to solve it. So don't worry about how I got x. I just got x. Because I'm good like that. Okay. So then I would just do pH is equal to opposite the log of my hydrogen, which is 0.0145 molar, and then my pH would be equal to 1.84. Again, are we concerned with this problem? No. Just wanted you to see that with H2SO4, if it's more dilute than 1, I can't ignore the presence of that second hydrogen. I have to include them together. Yes, sir?
Why does the H positive equal 1 point when it does 10 to negative 2?
Because this was my original that I got. And then plus X is the amount I got the second time.
That's what I thought.
Does that help? Okay. We good?
No.
Okay. Sorry. Okay, the next thing I like this next section a lot. And when I like it, I like teaching it. So this is gonna be fun.
Okay, so you
We're good now? All right. So now, moving on. Okay. So now we're going to talk about the acid-base properties of salts. Okay. So now we're going to start talking about salts. Now, every time an acid and a base react normally, okay, you're going to get some form of a salt. Okay. Now, does that mean every time an acid and a base react, we're going to get NaCl? No. Okay. Remember, we talked about last year how when I say salt, you can't think NaCl, and that's the only salt that exists on the planet. Okay? That is not the only salt. All right? Remember, salts are when I've got that positive ion bonded to that negative ion. Okay? When I have a metal bonded to a non-metal. Okay? That is when we have the salts. Salts are not always neutral. Okay? Salts are not always neutral. Sometimes we'll get an acidic salt, sometimes we'll get a basic salt, and sometimes we will get a neutral salt. Okay, so let's talk about this. Okay, neutral salts will be formed when we have a strong base reacting with a strong acid. Okay, so when I take a strong base with a strong acid, then I know that my salt is going to be neutral. For example, NaNO3. Let's talk about this, okay? The Na came from the base. How do I know that it came with the base?
It was probably bonded to hydroxide.
Because it was bonded to hydroxide, okay? So the Na came from NaOH, okay? Where did the NO3 come from? HNO3. So when those reacted together, okay, what I got was water. Does everybody see how I got water? Okay. Plus NaNO3. Does everybody see that? Okay. So if I have a strong base plus a strong acid, I'm always going to get water as a product. And then I'm going to get a neutral salt. Do we see how we could tell that that salt was neutral just by looking at it? I've got to say, where did the Na originally come from? Where did the NO3 originally come from? Were they both strong? Was one strong? Was one weak? And then you can figure it out. We'll talk about here. Okay. Basic salts, okay, are salts that are formed from a strong base reacting with a weak acid. So what to remember here is that strong always wins. Okay, so strong always wins. So think about it like if I was to get in an arm wrestling match with like The Rock or something, okay? I can pretty much guarantee you that every time we got in an arm wrestling match, I would lose. I think we can all agree with that, okay? Why? Because he's a lot stronger than I am. Okay, I'm a little weakling. He's strong. Strong always wins. Always. Okay, think of it like that. So what do we mean by that? Well, let's look at this. This salt. K2C2H3O2. Now what I like to do is divide them up into ions. Okay? So I know that this is my acetate ion, C2H3O2 negative. Okay? And I know that K is what? Potassium, which is K positive. Okay? So my positive was obviously bonded to my what? Hydroxide, which is negative, which made those charges cancel and just gave me KOH. Do we see that? Okay. My acetate was bonded to my hydrogen, okay, which made those go away. KOH is what kind of base? Strong base. Acetic acid is what kind of acid? A weak acid. So the salt that I get, my K2C2H3O2, is going to be what? It's going to be a basic salt. Do we see that?
I don't see how my KOH.
Hold on.
I don't see.
You don't see what? I'm going to rewrite it. That's why I
I
erased
don't
it.
see anything. Yeah, I didn't see the KOH and all that stuff.
So you know that like the C2H3O2 will bond to the H because H is positive and that's negative?
Yes. So divide this into your ions, okay? I know, or I should know from last year, if you studied this polyatomic ion, Spencer. All right. I should know that I can separate this into, I should recognize that C2H3O2 is what polyatomic ion? Acetate. Okay? And C2H3O2 acetate is negative. So then I'm just left with a what? K. So I know that K on the periodic table is in column 1. So therefore it would be what? K positive, right? Okay. So what was bonded to what? With my bases, I have an OH negative or I have an H positive. Those are your only two choices with what makes something basic and what makes something acidic, right? Okay. So who did the negative obviously have to go with? The positive. So together they formed KOH. Okay. So who did the hydrogen obviously have to go with? The negative, right? So they formed HC2, H3O2. So then I say, well, KOH is a strong base because it's a metal in group 1 bonded to hydroxide. That makes it strong. And I know that this is not one of my 6 strong acids, so it must be a weak acid. So therefore, I know the salt that I get has to be what? Has to be a basic salt because strong wins. Does this make sense? Do we see it better now? Ish. Let's see. Okay, now here's what you have to remember when you see the salt. Okay, is I know that my K came from a strong base and I know my acetate came from a weak acid. So they're going to ask you to take that salt and write a balanced chemical reaction. Okay? So here's the second thing you have to remember. Strong is a spectator. Now those of you who did not have me for pre-AP chemistry last year are going to have to kind of do a little catch up right here now. Okay? What do we mean when I say something is a spectator ion? It gets crossed out for my reaction, right? Correct? Okay? So it gets crossed out for my reaction because it's a spectator, which means it doesn't change on either side of the chemical equation. So what I would do is say, since K came from the strong one, it gets crossed out. Okay. So what am I left with? I'm left with my acetate ion. Right? Yes? Okay. I know it's a basic salt because I just determined that. So that means I'm going to end up with OH negative on this side. So I added water. I ended up with OH negative. And then my product is going to be the weak acid because this will make sense in just one more minute, I promise. Okay. All right, so let's go to acidic salts next. So acidic salts are going to come from we have a weak base reacting with a strong acid. Okay. like NH4Cl. Okay, I should look at the NH4 and say, what did it come from? NH3, which is a weak base. Where did the Cl come from? HCl, which is a strong acid. So I know NH4Cl is a acidic salt. Okay. Strong is a spectator, so the Cl went away in the problem. Do we see this? So I've got NH4 positive plus H2O. So what happened? I got H3O positive, which I know had to have formed because we said it was a what? Strong acid, right? And so then I get NH3 as my other one, which was the weak base. Okay. Don't let it overwhelm you. It will make sense tomorrow when we start right here. Oh, Tuesday. All right, we're out of school tomorrow and Monday. So I will see you Tuesday.
We don't have a
Oh, and you have homework this weekend, so hold tight. I'll give it to you.